as usual, I got cut off. So here's part 2 of number 10. As I was saying, the gravitational potential energy at the top gets transformed into some kinetic energy, but some of that gravitational potential energy gets sidetracked into the work that friction is doing. And we remember that work is equal to force times distance. So for a very steep hill, the distance traveled along the hill is equal to the drop in height, or closer to equal to the drop in height. For steep hills, big theta d is smaller. And for shallow hills, small theta, small angles above horizontal, d is larger. So the larger the d, the bigger the work done by friction, and the more of that starting gravitational potential energy gets sidetracked into the work done by friction. Next, number 12. Water balloons are tossed from the roof of a building, all with the same speed but with different launch angles. Which one has the highest speed when it hits the ground? Ignore air resistance and explain your answer. So in this case, we're going to think through this using conservation of energy again. Even though we've really only hinted at conservation of energy, I think it's such an easy to understand concept that we're going to go ahead and start talking about it now. I hesitate to say easy to understand, but I think it's the concept of conservation of energy is something that we've already thought a lot about living on Earth as people, especially AP Physics students. So water balloons are tossed from the roof of a building, all with the same speed, but with different angles. Which one has the highest speed when it hits the ground? So if I consider the energy held in that balloon, whatever it is, at the top of the building, whatever its launch angle is, there is, because of its starting velocity, it has some kinetic energy. But it's also up here, up high on the building, some distance h or y, and so it also has gravitational potential energy. Oops, I pushed my paper off the screen. So gravitational potential energy because of its height, kinetic energy because of its launch angle. It then goes up into the air, losing that kinetic energy, gaining gravitational potential energy until it turns around and comes back to the ground. Just before it hits the ground, the moment before it hits the ground, it has just tons of kinetic energy. It's all kinetic energy. So we consider, how might these water balloons have different transformations? Well, they all start at the same height, so they all have the same gravitational potential energy at the start, and they all have the same speed, so they all have the same value of kinetic energy. And here's where that weirdness of, because the velocity is squared in kinetic energy is not a vector and direction doesn't matter. So they'll spend different amounts of time. If it's a very steep launch angle, it'll go way up high before it turns around and comes back down. And if it's a very shallow launch angle, or even if it's heading down towards the ground, it will spend very little time in the air. But in all cases, we have the same starting combination of kinetic energy and gravitational potential energy. And we have exactly the same kinetic energy at landing, so we have the same speed at landing. Experienced hikers prefer to step over a fallen log in their path rather than stepping up on top and stepping down the other side. We should explain why. Actually, I've been hiking for most of my life, and I had no idea this was the case, but I guess I've been doing it all wrong. So I don't think I can draw this. No, I don't think I can draw it. But you can imagine the center of mass of the hiker. And so we're so glad we talked about center of mass. The center of mass of a person who's standing upright is about at their navel. So if you step over the fallen log and you sort of keep yourself upright, your center of mass essentially doesn't change. It does not go up and back down again. And so you have to expend less energy. Your body has to do less work because it has not lifted and lowered your center of mass. Instead, if you step up on top of the log and then step down on the other side, your leg muscles have to lift your center of mass up however high the log is, and then lower you back down, or maybe you just hop down. But in any case, you expend less energy, you do less work if you step over the log. Of course, if you step over the log and you're hiking in the California woods, I suppose this is true in the Utah woods too, and you're not looking carefully on the other side of the log, the park rangers always told us that you might step on a snake. I don't know. That probably doesn't happen to very many people. Okay, so now we're on to the misconceptual questions. These are those questions where you choose the correct answer, but the questions are asking you something that's supposed to get to a common misconception in physics. So number 1 says you push very hard on a heavy desk trying to move it. You do work on the desk, whether or not it moves, as long as you're exerting force, only if it starts moving, only if it doesn't move, never the desk does work on you, or none of the above. The correct answer to this is only if it starts moving. So we have to be careful that we're saying work on the desk. The force of your push only does work on the desk if the desk moves. There may be internal work happening on you in your body as your muscles contract and release, and that may cause your body to heat up and your body to burn calories, which is essentially a rating for how much chemical potential energy is being transformed as your body does things. But there is no work done on the desk. We talked about this in class, actually, so I hope everyone answers this correctly. When the speed of your car is doubled, by what factor does kinetic energy increase? And of course, we now understand that kinetic energy is half mass speed squared. So if you are doubling that velocity, that doublingness goes inside of the squared, and 2 squared is 4, so you end up with 4 times half mass speed squared. So you end up increasing your kinetic energy not by 2, but by 4. I think we also talked about this question in class. A car traveling at velocity v can stop in a minimum distance d. And so we're thinking work done in stopping is equal to the car's change in kinetic energy. What would the car's minimum stopping distance be if it were traveling at twice the velocity? So we're thinking force times distance, half mass. Ending speed squared minus starting speed squared, it comes to a stop. So that becomes negative half mass times starting velocity squared. So we're looking at starting velocity versus sliding distance, assuming that the force causing it to stop is the same in both cases. If I double that starting velocity, same as the previous question, I am quadrupling the kinetic energy held in that car. So if I quadruple the kinetic energy held in that car, the work done to stop the car has to quadruple. So that means I should slide 4 times the distance. Finally, a ball is thrown straight up. At what point does the ball have the most energy, ignoring air resistance? So we imagine a ball at the start of its path. It's thrown up, say speed v. It goes up into the air and it loses velocity, getting smaller and smaller velocity vector. That velocity vector doesn't actually look smaller until it pauses, and it then falls back down, regaining the velocity that it lost. Right? We've been talking about that since the very beginning of the year, free fall. So at this starting point, we can say y equals 0. We can say that there is no gravitational potential energy and all kinetic energy, right? It's all moving energy and no being high above the ground energy. As it goes up into its path, we trade kinetic energy for gravitational potential energy. Now it has some gravitational potential energy and slightly less kinetic energy. Now it has even more gravitational potential energy and way less kinetic energy. And here it is all gravitational potential energy and no kinetic energy because velocity is 0. All of the time, the total energy at each point adds up to be the same. So everywhere, the energy of the ball is the same, as long as there's no air resistance. The end.